Hi, welcome back. If you look at the whiteboard on the screen, you'll notice the number is changing from 4.x to 5 point, in this case 1. That means that we're changing gears a little bit, and in this case we're going to the discrete time Fourier series. We had been talking about the continuous time Fourier series. Now, we are not going to cover the DTFS in as much detail as we did for the CTFS. I'm not going to show you as many proofs and the construction. I'm not going to show you those details because many of them are very similar or the same as the CTFS. And it's just not worth our time to cover those details again. I don't want to give the impression that the DTFS is any less important than the CTFS. That's for some reason continuous time is so important and discrete time is not. No, that's not the case. It's just that we covered the CTFS first, and so now we're not going to cover the DTFS in as much detail. There are some important differences though, and it's those differences that I want to concentrate on. So let us take a look. Okay, the big difference, or the cause of this difference, is that frequencies differing by a multiple of 2 pi in discrete time are the same frequency. That's the key. Now, recall in continuous time, the goal of the Fourier series was to be able to write a periodic signal, x of t, as an infinite sum, or just a sum, of weighted harmonic components. So if x of t had a fundamental frequency omega 0, then k is the kth harmonic frequency. And so we add up all of these oscillations with some certain recipe, right? The AKs, which give the magnitude and the phase of the harmonics. We add them all up and out pops our periodic signal, a square, a rectangle, a triangle, whatever. So we wish to do something similar in discrete time. Now, first of all, I want to point out that if, in discrete time, if ak e to the j k omega 0 n, now, if this is a component, then so is an integer multiple of the period ak plus rn, where n is the period of the signal and r is an integer, times e to the j k plus rn omega 0 n. Okay, so that's the claim. So if we have this ingredient in our signal, the claim is that we also will have the second ingredient there. So why is that? Well, it comes down to the one of the first things I said in this video, and that is that in discrete time, frequencies that differ by an integer multiple of 2 pi are the same frequency. You have to remember that. So let's take a look. If we have a sinusoid of this frequency, right, the k plus rn frequency, or harmonic, then if I use properties of exponents, I can write this as e to the j k omega 0 n times e to the j r n omega 0 n. And again, r is an integer, and n, capital N, is the period of the signal, x of n. Now, if you remember, in discrete time, the fundamental frequency is 2 pi over the period. So n times 2 pi over n is just 2 pi. So that term there is just e to the j times some integer times 2 pi times n. And n is an integer, right? 0, 1, -1, whatever. R is an integer. And so this is e to the j times some integer times 2 pi. And so this is exactly equal to 1. And so we get e to the j k omega 0 n. So remember the claim? The claim was that if this is an ingredient in our construction of x of n, then so is this. So that means we don't want to add the same ingredient twice. So we're not if we're going to add this guy here, we're not going to add this guy here. So we need to be careful on the way we handle that. So, and we could prove it, but again, I'm not going to show you the gory details here like I did in continuous time. Our analogous equation to this guy up here is that xn equals, we're not going to sum from minus infinity to infinity. We're not going to add up an infinite number of harmonics like we did in continuous time, because that would be double counting these frequencies that differ by an integer multiple of the period, or triple counting or quadruple counting. We're simply just going to add up over one period. And so here's the notation. You can pick any k's you like, but you have to go over one full period. Okay, one full period. That's it. AK e to the j k omega 0 n. So other than that, this equation is what you might expect. When you transition from continuous to discrete, the everything else here is the same. So we have the t becomes an n, right? The t becomes an n, and everything else stays the same, but we're summing over one full period, not infinite harmonics. So we don't want to double and triple count. Now, observe what that means then. Let's look at the Fourier series coefficients then. If ak is the coefficient in front of e to the jk omega 0 n, and ak plus rn is the Fourier series coefficient in front of this harmonic k plus rn, and if that's the same ingredient, then it must be true that those two things are the same, right? If the harmonics are the same ingredient, then we have to have the same amount of those harmonics. And so what is this? Well, this tells us that a shift in k gives us back the original series. So that means that the Fourier series, the discrete time Fourier series, is necessarily periodic. It too is periodic, and with period n. That is something that we did not see in continuous time, all right? But it must be true in discrete time, all due to the fact, again, that frequencies differing by an integer multiple of 2 pi are the same frequency. And in this boxed equation that I have over here, this is called the synthesis equation. Just like we referred to this in continuous time as the synthesis. So which one do we mean? Well, it'll be obvious if we're talking about discrete time or continuous time. So we call those both the synthesis equation. Give me the ingredients and I will synthesize, or I will reconstruct x of n. Okay, synthesize means to kind of artificially build or construct. And how do we get the ingredients? Well, again, I'm not going to show you the proof. They're in textbooks on the internet. It's very similar to what we did for continuous time. And I'm just going to write it out here. Okay, and we'll put a fancy box around there. And this is how we get the ingredients. This is called the analysis equation. And remember, in continuous time, we had something similar, 1 over t times the integral over one full period of, that should be ak. ak is equal to 1 over t times the integral over one full period, x of t, e to the minus jk omega 0 t dt. So this equation now in discrete time is exactly what you would expect when you go from continuous to discrete. The integral becomes a sum because integration does not make sense in discrete time. So instead of integrating over one full period t, we're summing over one full period n, and we've got 1 over t becomes 1 over n. X of t becomes x of n, and e to the minus jk omega 0 t becomes e to the minus jk omega 0 n. And in continuous time, we call this the analysis equation. And in discrete time, we're going to refer to this as the analysis equation. It will be obvious which one we're talking about. So what does this say? Well, give me x of n, and I will analyze it, or I will figure out the ingredients. I'll deconstruct it and figure out the ingredients. Okay, so much of this is the same as what we did with continuous time. All right, but let us look at now some examples. Given a periodic discrete time signal, can we find its Fourier series? Let's have a look.